Hi, good morning. All right, so this week we're gonna go over the design of cams and followers. So the next two lectures are gonna be really important in your exam number 5, I believe. So the first one is called CEP. Yeah, it's only one more exam. I forgot it's 5 or 4. I think it's 4. Yeah, don't panic. I think that's my mistake. So in this lecture, we're going to talk about CEP. And then the next lecture, we're going to talk about critical path motion, CPM. I already posted the video on YouTube. Please check it out. And this morning, I also post homework number 6 online. And then this number 6 is going to be really similar to your exam. So once you watch these two videos, make sure you solve your homework 6. I'm going to post the solution on next Wednesday, and then you're going to have enough time to review the solutions before the exam. All right, so CEP. So first thing is, what is the purpose? Like, what is our objective when we talk about CEP design? So in the previous lecture, we mentioned about 4 different things: S, V, A, and J. So displacement, velocity, acceleration, and jerk. So they are the motion of followers. So we used 4 diagrams to describe the motion of your follower. But then these velocity, acceleration, and jerk, they're different because they're not functions of time, they're functions of theta. So the theta is the angle of cam. So you plot the displacement or the motion of your follower as a function of your cam. So eventually, when we talk about cam design, the objective is we want to find the S theta, which means we want to find the displacement as a function of theta. So that's what we want to find. And then there are a few design requirements. So the first one is A theta is continuous. So last lecture, we discussed that we don't want like a discontinuity in your acceleration, because once there is a discontinuity, that means you're going to have an impact force between your cam and follower. So this impact force is going to damage the surface, the contact surface. Okay, so that's one thing. Your A theta should be continuous, and then your J theta should be bounded. So when we say it's bounded, that means your J theta value is all, you can find two limits that enclose your theta values. So there is no infinite values in your theta, in your J theta plot. And then we already mentioned that these two conditions, they're equivalent. So if one of that is satisfied, then the other one is automatically satisfied. So usually we only focus on the first one. We want to make sure your acceleration diagram is continuous. So that's the really strict requirement. So we also have some other requirements. For example, your acceleration should be minimal. If your A is like minimal, that means you only need the smallest amount of force to drive the system. But then these are, I should say, it's like more desirable requirements. It's not one of these necessary requirement we're talking about. So most of the time during the exam, we only focus on these necessary requirements. But in practice, you also want to target for example, you want a small variation in your A, you want small amplitude in A, but then it's really hard to achieve these requirements by hand. So at that time, you're gonna need a MATLAB, and then you're gonna need the fmincon to minimize that optimization target. All right, so that's the design of your CAM. That's the logic behind the design. So for CEP, everything is simple. So we only target your S. We don't care about V, A, and J. We only design CAM for a system such that your S follows a certain path. So why this is simpler than other cases? That's because you're going to see, if you watch the video, then you're going to see 3 different domains discussed in this CAM design. So we're talking about time, theta, and x. Okay, so we already know the theta's meaning. So theta means this angle of the CAM. So S, V, A, J, they're all in the theta domain. And then eventually your design is presented in a theta domain. So that means your theta is a domain where you output your design. So I would say that's your output domain. But then usually when you get when your customers talk to you saying, okay, I want to design a CAM that output certain velocities. So they're gonna give you those design requirements in time domain. For example, I want 10 meters per second. I want in 1 second, it reaches 10 meters. In the next second, it maintains in 10 meters. So that means your time domain is more like your input of your design. So you got these from your customers, and then that's why we also care about time domain. So X domain is something between T and theta. We're gonna see these later in CEP design and also in CPM design. So the tricky thing is, how can we dump information between these 3 domains? That's the challenging part for CAM design. So once you understand these, then the other part is just solving linear equations. All right. So the good news is for CEP, because S is a displacement. Remember that the unit for displacement is like meters. And then your S is a function of theta. So that means in your S function, you only have displacement and theta. So there is nothing about time in the discussion. So that's why I'm saying that CEP is simple, because in CEP, you don't have to worry about the time at all. You can directly dump things. You can directly transfer information between theta and x. All right, so I'm gonna use an example to go over this. So example number 1, we're gonna design a CAM following the CEP, the following requirements. So it first dwell, and then it rises up, and then dwell, and then fall. Okay, so that means you're gonna see 4 different steps in your, let me see. Let me try to mute everyone. Oops. All right. So that means we need to design 4 different segments. So in this case, everything is given in degrees. So that means we already know the inputs in the theta domain, right? So we don't even care about the time domain. So that's good news. So the first step when you design a CAM is you want to draw your S, V, A, J plot based on the information you get from the problem description. So in this case, you first draw your S theta function as a function of theta, and then you just draw. Okay, we have 1, 2, 3, 4 different segments. The first segment is from 0 to 90 degrees. So usually I recommend you to use radian. And then your theta, the second segment is another 90 degrees. So that means it ends at pi, and then there's 3 half pi, and then eventually 2 pi. So that's how you find all the segment boundaries. And then the first one, dual, at 0 displacement for 90 degrees. So that means the first 90 degree, it maintains 0 displacement. And then the second segment is, it rises up from 0 to 25 millimeters. So let's for convenience, let's say h equal to 25 millimeters. And then for the rise, we don't know how it rises up. Is it rising up linearly or in a second order function? We don't know. But then what we know is the boundary condition. So we know that it starts from 0, it ends at 25 millimeters, but whatever in between is a question mark. So that means we need to design that question mark. Okay, so the third one is dual again, 25 millimeters stationary. All right, so after that, again, it's gonna go back to 0, and then we know the boundary conditions, but no intermediate information. All right, so 1, 2, 3, 4 segments. So usually, for cam design, we're gonna use piecewise linear equation. Describe as theta in a piecewise function. So that means you're not going to find I'm going to use a different color, purple. You're not going to find a single function that describes the entire motion. Instead, you're going to target segment number 2, segment number 4 individually, and then lump them together using piecewise functions. All right. So that means usually for CEP design, the dual is very similar. It's very simple. So because it's a piecewise function, that means we need to find S theta, F theta. Let me use a different symbol. We need to find S theta 1, S2 theta, S3 theta, and S4 theta, right? Because it's a piecewise linear. The first segment is from 0 to half pi. And then you can directly get the information, right? It's flat and it's a constant 0. And then you also know that in the third segment, your theta is from pi to 3 half pi. And then it's h, which is 25 millimeters. So then we just need to find what's in between. So this S theta is your output, is eventually your cam design. So then what is the second segment and what is the last segment? All right. So the easiest design is actually just by connecting these dots using a linear line. It's so natural. So why not just using that? So you have to always remember, keep in mind that there is a strict design requirement, which is your A diagram should be continuous. So if you directly connect this line, let's focus on the S2 theta. Your S2 theta should be 2h over pi, right? So that's your slope, K is 2h over pi times theta minus half pi. If you use a linear function, that's your S2 theta. So once you design your S, you should always check your velocity and acceleration. So if your displacement is a linear line, then what you have in your velocity, v theta. So in the first segment, it should be flat at 0. In the second segment, you're going to have a constant velocity, and then this is your k, right? Which is the slope of this line. And then if you want to draw your acceleration, a theta. So in the first segment, because it's flat, it's all 0. In the second segment, it's also flat. But then you have to pay attention to the switching point here. At this location, your velocity suddenly changes from 0 to a constant non-zero number. So that means your acceleration at that point is actually positive infinite. So that's why it's not continuous in acceleration. So CEP is not as simple. CEP design is not as simple as connecting lines. So that's my point. So you need to actually think more, trying to make sure your acceleration is continuous. So how can we make your acceleration continuous? So the very first approach is, because we already know that your acceleration should be continuous. So why not just start your design from acceleration? Give your acceleration a continuous function, and then we start from there. So that's the background for these sinusoidal cam follower design. So what we do is, since we already know that, let's go back to these again, and then let's forget about all these information. Let's go back to S, V, and A to see what we already know. So we already know that in these segment 1, 2, 3, 4, in segment 1 and 3, oops, your velocity is 0. And then your acceleration is also 0, right? So that's what we already know. And then let's first focus on segment number 2. Because we already know that the acceleration should be continuous. So that's why, okay, let's just directly give you a continuous function, a sine wave with an amplitude of c. And then this is from half pi to pi. And then can describe this sine wave. So your a theta, what is that? So your a theta is going to be, so at this point, you're going to see why we need an x domain. So right now, your sine wave is not starting at theta equal to 0, right? So that means if you want to describe your a theta, it's going to be a c times sine, whatever, omega t plus some phi. So this phi is your phase delay. So you need another theta angle to shift this sine wave back and forth along the theta axis. So that's not convenient. So usually what we want to do is, you should, so we hope there is another coordinate system which starts at half pi and ends at pi. So we name these coordinate system as x, and then this is your ax. So basically your ax, your x coordinate is just it's another local coordinate system. So this x helps us to more easily define your sine function. All right, so what are these x, in this x domain, what properties we have? Let's see. So when theta equals to half pi, we want your x equal to 0. When theta equals to pi, we want your x equal to 1. And then let me write it out in this way. That's your theta domain and x domain. And then between x and theta, all the intermediate steps is a linear transformation. So that means we're stretching your x coordinates linearly. So a reasonable assumption for these is we assume your theta, the first theta angle is theta naught. That's where your theta starts. And then the next theta angle is theta 1. That's when your theta ends. So we assume there is a beta, which is theta 1 minus theta naught. Your beta is basically the width of the segment. In this case, your beta is half pi. Okay. So the way we find x is your x is theta minus theta naught over beta. So you can see that your x is a linear function of theta, right? Because the slope is 1 over beta. So that means you're stretching your x-axis. You're stretching your theta axis by 1 over beta so that your theta becomes x. All right, so that's the benefit. That's how we get your x coordinate. So once you have this x coordinate, your segment 2 is no longer in half pi and pi. Let's draw it out. So you have your x, you have your ax. As we said, it's no longer from theta naught to theta 1. It's actually from 0 to 1, right? And then we know that this is your sine wave, and then this is your amplitude c. So in this case, that's how we get ax equals to psi. And then we know the period is t, is 1 second, is 1. So that means your omega over 2 pi is 2 pi over t. So that means your omega is 2 pi. So it's 2 pi is 2 pi x, and then there is no phase lag. So it's directly 2 pi x. So that's how you get your ax equal to sine 2 pi x. Oh yeah, exactly. Okay, yes, you're correct. So this should be theta because your a is a function of theta. Actually, this omega is different from that omega. So these, let's name it as omega prime because that omega is the frequency in theta domain. All right, so once you find your ax, so you can easily get your a theta. Your a theta will be sine 2 pi x. You replace your x by theta. So it's 2 pi times theta minus theta naught over beta. So that's how you get your a theta. So once you have a theta, you can find your v theta s theta by integration, right? Oh yeah, it should have a constant. I forgot the amplitude. So that's how you find your a theta. So if you don't want this x intermediate step, you can actually directly find your a theta from this curve. So let's directly find it out. So here, the other case is when you start from theta naught, it ends in theta 1. And then we know that this is half pi, this is pi. And then we want to find your a theta as a single sine oscillation, amplitude c, that's your a theta. You can also get these without using the x domain. So what you do is you already know that your a theta is c times some omega prime theta plus phi, right? That is your A theta in the theta domain. And then your omega prime over 2 pi. So that's your T prime in theta domain. That's your period. So in this case, your period is no longer 1. It's actually pi minus half pi. So that's half pi. So that's why your omega prime equals to 4. You would have your A theta equal to C sine 4 theta plus 5. And then how to find these 5? These 5, you can easily find out that when theta equals to half pi, this acceleration value should be 0. So that's how you find your phi. The other way to find your phi is that, okay, you see that your entire function is shifted to the right by theta naught degree. So the other way to find your function A theta is C sine 4 C minus theta naught. So that's how you shift your entire sine function to the right by theta naught. So that means you can also get your A theta directly from your theta domain without using any x. So once you have your A theta, then you can get your V theta by integration. And then your S theta is another integration. So let's count how many unknowns we have. So in this case, your A theta has only one unknown, C. Okay. But then after one integration, that's going to introduce a constant because it's an indefinite integration. So you don't know the boundaries. So you have to put a constant after that. And then you're going to put another constant after the second integration. So 1, 2, 3. Typically, you're going to have 3 unknowns. That means you need 3 equations. So that's when we need to go back to the boundary conditions. So for the segment number 2, you know the velocity should start from 0 and it ends at 0. Your displacement starts at 0, ends at 25 millimeters. So you have 1, 2, 3, 4 boundary conditions. That's going to give you 4 equations. You have 4 equations, 3 unknowns, but then one of the equation is going to be redundant. So that's how you solve for all these unknowns. So you can find these details in my notes posted on Blackboard. And then you can implement the same method to design your segment number 4. But then actually there is another trick. So eventually your S will be something like this. And then because the width of this segment is the same as this one, so theoretically, your segment number 4 should be symmetric to your segment number 2. If you know that trick, that can save you some time. So this is how we use sinusoidal function to design your S theta. So for CEP, if you want to use sinusoidal function, it's better to start from acceleration because we know that acceleration should be continuous. So that's why at the beginning, we directly give an acceleration a continuous function. And then we integrate back to the S domain. And then based on the boundary conditions, we can determine the constants introduced in this method. So if you use a sinusoidal function, you're going to get an okay design. It's not the best design. The reason is the acceleration amplitude C is going to be large. So there are other methods that can help you to reduce the amplitude of acceleration. So most commonly, we're going to use a polynomial displacement assumption. So in your exams, that's the only one you're going to use. All right, so here we assume that your displacement is in a polynomial format. And then in here, your polynomial is not defined in theta, instead is defined in x. Okay, so what I'm saying is, in your exam, I'm not gonna test you how to use the sinusoidal function to design CAM. You only need to use polynomial displacement, which is I'm gonna discuss right now. All right, the same thing, S, V, A, and J. Your S, V, and A should be continuous. And then we want to find the S such that it follows the steps follows the prescribed displacement. You have theta, the first 90 degrees flat, 180 to 270 is another flat value. You have your H, you have S theta. All right. So no matter which method you're using, the first step is always draw the SVAJ based on whatever information you have. Oops. Let me clear that page. All right. So that's your S, V, and A, and J. So in this lecture, we're not going to talk about J. But in your future designs, you might have to deal with J if the customers ask for certain J requirements. So the first segment, your velocity is 0. Third segment is 0. Acceleration is the same thing. All right. So in this case, let's focus on segment number 2. So whatever you know, so in this case, we know the boundary conditions of your S2. So you have theta equal to theta naught, that's theta 1, oops, equals to half pi, that's when you have your S theta naught equal to 0, V theta naught equal to 0, A theta naught equal to 0. So that's the boundary conditions you have for theta naught. And then you have your theta equal to theta 1, that's full pi. And then in this case, you have 3 more boundary conditions. Is H. Oops. You have your V theta 1, 0, A theta 1, 0. All right. So as we mentioned before, you can easily couple theta with your X domain by using X equal to theta minus theta naught over beta. And then beta again is theta 1 minus theta naught. So that's all the information you know based on the problem description. And then we make a very strong assumption, means we know that your Sx should be a polynomial function. So that means your Sx is a polynomial, I equal to 0 all the way to n Cixi. If you don't like the summation, I can write it out. It's C naught constant plus C1 linear, second order, all the way to nth order. All right. So so we assume that Sx that's in segment number 2. We know that segment number 2 is going to be a polynomial, something like this. Okay, so how can we find this polynomial? So in order to find this polynomial, so we just need to find out all the coefficients, right? C naught all the way to Cn. But then how many C's we should assume? That's the next question. So what that n number should be. So here, let's say we in total is from 0 to n, we have n plus 1 unknowns in Sx. How many equations we can get for Sx? So that's actually from the boundary condition. So let's see here, we have 1, 2, 3, 4, 5, 6. You can easily find 6 functions for your polynomial. So that's why we need 6 functions. We have 6 functions, and then we have n plus 1 unknowns. So then naturally, you want to select your n equal to 5. So you have enough functions to solve your boundary to solve these coefficients. All right, so let's see. You have your Sx equal to C naught plus C1x plus C2x squared. So up to this point, we know, okay, we need 1, 2, 3, 4, 6 terms in your S. And then you can calculate your Vx. Your Vx is ds with respect to dx. So that's a C1, 2C2x plus 3C3x squared plus 4C4x3 plus 5C5x4. Okay, but so that's how you get your V in X domain. But then remember that all the boundary conditions are given in theta domain. So how you connect your Vx to V theta? So that's our next question, right? So by definition, your V theta is ds d theta. Your Vx is ds dx. So we want, if you compare these two, we actually want to replace the x in the denominator by d theta, right? So what we do is you can easily multiply d theta on both, on top and on the bottom. Then let's circle these out. Your ds d theta, these two together gives you ds d theta, and then you have d theta dx after that. And then the first term by definition is v theta, and then we need to find the second term. What is your d theta dx? And then remember, your x equal to theta minus theta naught over beta. You can do derivative on both sides. Your x becomes dx. Your beta and theta naught, they're constants, so you don't have to do anything. The only thing varying is the theta. So you have d theta times 1 over beta. So from here, you can see that this equals to beta. So that's for CEP design. So because the polynomial is there, the polynomial is defined in X domain, and all the boundary conditions are given in theta domain. So that's why you need that additional step to connect these two domains. So if you go to lecture 20 for the CPM design, so all the boundary conditions are given in time domain. So that transformation is even more complicated. So you actually need to multiply another dt over dt to get the relationship. All right. So in this case, we know that your Vx equal to V theta times beta. But then the good news is all the velocities are 0. So that means your Vx equal to 1 equal to V theta equal to theta 1 times beta. So that's 0. Vx equal to 0 equals to V theta equal to theta naught times beta. That's also 0. So why I have this is because when x equal to 0, that's when your theta equal to theta naught. So we evaluate the function at the same time point. All right. So we know Sx, we know Vx. Then we need to calculate Ax. Your Ax is just one more time derivative with respect to x. So that's 2c2 plus 6c3, 12c4, 20c5. So again, you need to find out your, so you need to connect your A theta with AX because all the boundary conditions are given in theta. And then we need to use boundary conditions in X domain to solve these polynomial equation. How can you find that? Similarly, using the chain rule, your A theta is ds squared d theta twice. Your Ax is dx squared twice. So what you do is dx twice, d theta twice. Oh, sorry. Then you can see that is just simply v theta times beta squared. Oh, sorry, that's a theta. All right. So then you can transfer all the boundary conditions from theta domain to x domain. So we want to find a when x equal to 0. So if x is 0, that means your theta is theta naught times beta squared. And then luckily all the accelerations are 0, so it's 0. The same thing, you can find the other boundary conditions as theta equal to theta 1 times beta squared, also 0. So this example is very special because all the velocity and acceleration, they are 0. So that's why you have the same velocity in both x and theta domain. But then if you go to lecture 20, and then in that example, your velocity at the boundary, they're not 0. So then you have to pay attention. All right, so let's see. Let's count all the equations we have. For displacement, you have x equal to 0, equal to x equal to theta naught. So that's 0. That's your h. You have equation number 1, number 2, 2 equations from displacement. And then 3, 4, 2 equations from velocity. 5 and 6, 2 equations from acceleration. So you have 6 equations in total, and then you have C naught all the way to C5, 6 unknowns. By solving these 6 linear equations, you can find your coefficients. So that's how you find your segment number 2. You can implement the same method to find the solutions for segment number 4. And then I already post the solution on Blackboard. So you can compare your solution with mine in the end. So a few things. If you're interested, you can actually compare your A theta plot calculated from these polynomial methods. You can compare these to the previous A theta from a sinusoidal assumption. You can see that actually this A theta has a lower amplitude. So that's why polynomial function is usually better than sinusoidal function. So you can actually think about these opposite class. So what if your S theta in the third domain is not dual? What if I'm giving you a slope, and then this slope here is 1, or I should say, and the end of this S3, you have another H1. Your H1 is going to be, let me erase that slope. It's going to be like 50 millimeters. Trying to think about that. Can you deal with that? If it's no longer flat, can you find your polynomial for segment 2 and segment 4? So the hint is in this case, you're gonna need to change your boundary conditions, right? Because in this case, your velocity here is no longer 0. So in the third domain, you actually have 0. You have a constant velocity. This is the slope of this. Okay. And then your acceleration is still 0. So that means you have to change your velocity at these points. That means this velocity is going to be k. Once it's not 0, then go back to here. It becomes k times beta, and then this value won't be 0. So please expect something like this in your in exam number 4. So the question will be really similar, but I'm going to change the boundary conditions slightly. And then so in this case, I'm giving you 90 degree, 180, 270. So all the segments are evenly distributed. So I might just give you different width of your segments. So that means in different segments, you might have different beta values. So I think I can give you an example. So by saying that is just saying that it might be really ambiguous. So let's see. Let's say I'm making slight changes to the example again. You have your theta, you have your S theta. We want to design such that in half pi, something like this. I should say 1/3 pi. And then here you have 3/4 pi. You have 3/5 pi, and then 2 pi. So in these guys, a similar profile. You have dual, you have rise, you have another dual. Then you have the fall. This is your edge equal to 25 millimeters. Can you find the polynomial equation Sx, or for this segment number 2, and then Sx for segment number 4? I'm going to use a subscript. So you can also think about these after class. Make sure you can solve the question. The hint is when you design for segment number 2, your theta naught is 1/3 pi, theta 1 is 3/4 pi, and then your beta is theta 1 minus theta naught equals to pi. When you design for segment number 4, your theta naught is something like this. Theta 1 is 2 pi, and then your beta is 1/3 pi. So you have to remember that your theta naught, theta 1, and beta, they will be different in different segments. So the example in this lecture is very special because so that means your beta are the same in different segments, but in practice, that's not always true. So you have to pay attention that make sure you calculate the beta in each segment individually. Let me see what else. I think I cover, hold on. Oh, the other thing is, okay. So after solving these SX equation, you're gonna find out the polynomial. In this case, it's from n equal to 0, I equal to 0 to n equal to 5. So CI XI. So the solution you're getting is SX, that's in the X domain. But as I said, we want as theta because that's the output we want. So you need to do one more step. Will the polynomial be symmetric? In this case, yes. Because the design itself is symmetric. So that means, yes, it is going to be symmetric again. But then how can you find the symmetric polynomial? So mathematically, that's also tricky. All right, so my point is from SX to S theta, if you want to solve your homework, solve your exams, you need to replace X by theta. Without that step, your solution is not 100% complete because S theta, this is the diagram you want. If you design SX, you just find the solution for the intermediate step. All right. So that's everything you need to know for CEP. Okay, how do we translate this? That's a good question. So I'm going to talk about these after exam, perhaps in the last week. So, all right, so that's it. Any questions?